Ladies and gentlemen, we've had some technical difficulties, so we're starting from scratch. We're going to talk about potential energy. And when we're doing this, we usually look at energy diagrams. We'll call potential energy PE from now on. Two potential energy diagrams where we have PE versus, most other books call it the reaction coordinate. What the heck are they trying to say? How about reaction progress? All right, and we have two types of potential energy diagrams. We have those that start with reactants up or low, down low, and they go up to reactants or products that are higher. Reactants and products, left and right. And do you remember if this one's an endothermic or an exothermic reaction? Endothermic. Endothermic. And the other one is going to start high and go low. Wow. At least it's writing for me. What do you call that one? Exothermic. And in an endothermic reaction, you have the potential energy definitely increasing, right? And because of that, and the law of the conservation of energy, what's happening to the kinetic energy? Energy of motion. Decrease. Things are going to get cold. That's what that means. Things will get cold. That's all kinetic energy is. If it's down, it's getting lower. If it's up, it's getting hotter. All right. And we have things like the delta H for a reaction. You guys, we've been calculating that, right? So if you have to do delta H, it's from products to the beginning, backwards to the beginning. And this one, delta H goes here. Kinetic is negative on this one. And kinetic is positive in the next one. Why? Because potential is going down. And that's leading to kinetic going up. Yeah, they don't know they're going to be on video. All right, and what do you, it's positive, right? Kinetic's going up is positive. Kinetic is heat. Exothermic, you know? Just trying to show you where these names are coming from. Negative means endothermic. Positive means exothermic. Now at the top of these hills, there's the symbol for what's called a transition state. Never draw the box first. I should have known that 20 years ago, but that's okay. Short form for transition state, TS. Also the initials of one of my favorite jazz musicians. Thelonious Sphere Monk. There you go. Had to get that in there. Yes. Okay, it's negative here because the potential energy is going up. Molecules are getting more stable, and as a result, the environment's getting more heated because you can't destroy or create energy. It's got to go somewhere. So that potential that let the products go higher had to be compensated for by the environment going the other way.
It needs heat energy, right?
And kinetic energy is heat.
Yes,
Potential energy is the stored energy.
yes. So
In the bonds, it's stored. It wants to be used, but you got to break the bonds to do that.
yeah, but endo it means like it needs energy. So it has to-
Endo takes within, yeah. The prefix endo means take in.
Yes,
The prefix exo means give out,
it means,
exude.
yes, but
Yeah.
endo it has to be negative, and the endo has to be.
Yeah, the delta H will be negative. Sorry.
has to
Oh,
be
kinetic.
positive.
Oh, wait. Oh, the potential is positive, right?
Yes, has
But-
to be positive.
Potential is positive. Here, let me write it down. I think you're confused because I didn't make this clear. Yeah, endothermic diagram has potential going up, right?
Yeah, yeah,
And exothermic diagram has potential going down. Okay? Negative. And the kinetics negative and kinetics positive because they have to go in opposite directions. We're going to focus on the transition state. Now, this morning's lecture, we went into a lot of detail. I'm going to summarize it here with highlighters. This energy level right here in the first diagram, is that energy level closer to the products, which are here, or the reactants? Yes, and he already answered yes, anticipating or comparing reactants and products. When the TS energy is closer to the product energy, I'm going to write this and type it. When the TS energy is closer to the product energy, then it is surmised, that's a good word. You're proposing something. Surmising. It's surmised that the TS appears more to look like the product than the reactant. Don't worry, I'm going to move this around, make it look nicer. We call this, now are the products at the beginning or the end of a reaction? End. What sounds like more like the end, early or late? Late. So we call this a late transition state. Uh-oh. And wow, that's supposed to be reactant. Yeah. Reactant. We call this a late transition state. Oh, that's catchy. And we're gonna go with the old 24-point font for things that are real important. And blue, and endo's blue. Baby blue is a little faint, but let's see what it looks like. And let's move it around. Not your favorite, doesn't show up very well. It's good, we like it. It is a nice color. And I want to make it on the left diagram, so here we go. I like that. Looks like a copy-paste job's coming. Copy, save, Control-T, paste. I don't think it's saved. We had this issue before. We lost a whole document before. At least it's writing. Dude, I got to reverse everything. I need serious editors out there who do not let me miss something, because I always miss something. When the TS energy is closer to the reactant energy, isn't that what's up on the diagram above, except the Q? Look, TS energy is closer to reactants energy. So whipping out the old highlighter. Closer to products, we made the statement below. Closer to reactants, we're about to make the statement. We're editing it right now. We just want to get in here. Reactants energy, then it is surmised that the TS appears more to look like the reactants then the, why are you doing this? Why? Product. We call this, we don't call it late. If you're a reactant, you're at the beginning, right? Call it early. And we should put some more emphasis on these things, you know. Yeah. Got the underlining. Maybe a color change. Dark blue. Nice. Yeah. Late. Underline. Okay, good. We never saved this one either. You better save. I'm threatening my computer. Things are desperate. Did it ever say save up here? I missed it. No, I'm worried. Okay, moving on. There's something called the Gibbs free energy equation. It's new to a lot of us in here. And it goes like this. Delta G, and that equals, and the thing we were calculating the last day was this, right? Change in enthalpy. So in green, we're going to say enthalpy. We're going to, in blue, we're going to say Gibbs free energy. Yeah. Gibbs free energy. Is that Jebediah Gibbs? No, it's not. It's the chemist Gibbs, not the NCIS Gibbs. I don't even know if it's Jebediah. Minus black sign digit. No, sorry. Minus. And T is heat, so it's hanging off. Yeah. And that's times delta S. T, forgot to mention this morning, that was temperature. And delta S is change in entropy. Entropy is just is how random things are. It's a driving force for many, many reactions, particularly reactions that create gas molecules. One of my favorites is combustion, where you have one octane molecule creating more than 10 gas molecules. So even if the octane was a gas, that one molecule created 10. What's more random, 10 balls flying around in a box or one ball flying around in a box? 10 balls flying around in a box, then that's what gases do. They're flying around. They're very random. It's the most random state of matter, right? So 10 gas molecules. So increasing gas molecules, best way to create entropy. Okay? Another way to make entropy is to take one molecule, break it down to 5. They don't have to be gases, just more molecules means more random, right? Another way is to take a liquid and boil it. Entropy where there's gases because it's more random than liquids. Liquids are down here flowing like this, right? Gases are like everywhere. That's random. I'm going to cut this story short because in chapter 8, we're going to say this, and you're going to have to say this on your test. In chapter 8, delta S, which I should do in black, is roughly 0 because the two propagation steps don't create entropy changes, and I'll go because on my because. Oh, how do you like that? It's always radical dot plus non-radical goes to, hello. Wow. We're gonna live with that thing? Get out of here. It's gonna happen, guys. I'm gonna say something I don't want to pretty soon. Yeah. They're both radical. And you really think that's still big, huh? Okay, fine. Radical plus non-radical gives non-radical plus radical. And states aren't changing. That's solids, liquids, gases. There's no change in states. I'm not talking about transition states. I'm just talking about states of matter. Okay? So the only thing you need to know about entropy is that right there, this thing here, you've got to tell me you're acknowledging that you know in chapter 8, delta S isn't changing, and look at the big equation at the top of the screen and simplify it for me when delta S is 0. What's delta G? Delta equal to delta H. There you go. So when delta S is 0, then delta G is roughly delta H. And the beauty of delta G is right here. Delta G predicts spontaneity. That's just a fancy way of saying, does it happen? It's either spontaneous, which means it does happen, or it's non-spontaneous. It does not happen, okay? Delta G less than 0 means spontaneous. Spell spontaneous right. And delta G greater than 0, non-spontaneous. If you want to make a non-spontaneous happen, you better give it another reaction that's more spontaneous than the non-spontaneous reaction is non-spontaneous. You got to overcome that. It's like a barrier. In biochemistry, it happens all the time. Like in the glycolysis, I think 3 or 4 of the steps are endothermic, but the other 7 steps drive it. Okay, they push it. Getting into way too much detail. Just remember this. This is important. We'll put it all together when we do our exam question, okay? One more fact before we get into a big exam question worth 25 points. One more fact. For us, for chapter 8, I got to keep adding that. More spontaneous means faster. So we'll do reaction 1 versus reaction 2. And let's say we have negative 36. Let's just say all of these are kilojoules per mole. And we're doing an example here. So I have negative 36 versus negative 22. Which one's faster? Highlight the faster one. Highlight the faster one. Which one you picking? If negative, less than 0 means spontaneous, then more less than 0 is more spontaneous. So the first one is faster, right? Highlight the faster one, which is kind of awkward, people, because chemists are only concerned with the slower one. So maybe I should say highlight the slower one, because we're always picking the slower reaction to study more intensely. It's the one that we need to manipulate to make the thing work better. Can I just change the question? Highlight the slower one. Here's where it gets harder, because you're thinking in double negatives almost. I still have to think about the faster one. More negative, faster. I go there every time. So the negative 36 is faster, so therefore, which one's slower? Negative 2, 2. Got it. And we're going to go highlighter and green. Okay, reaction 1, that's first example. And second example, we're going to go, we'll make one negative 21 and one positive, plus 4. And we'll do another example of positive 6 and positive 28. Okay. I think the next one's the easiest one ever, right? The negative 21 is very fast compared to the 4, right? So the 4 is slower. And green highlighter. Now both are slower than the original 4 reactions here, but we don't care about these 4. We care about this versus this. And you say, okay, which one's closer to a negative number because it's faster? 6 is faster. Which one's slower? 28. Slower reaction. So you can remember, the more positive it is, the slower. And it works even here, right? Because negative 22 is more positive than negative 36. You're saying, what's he talking about? They're both negative. But negative 22 is closer to 0, so it's more positive. Okay, that's it. Now I believe we're ready to answer all A, B, C, D, E, F, G, H, maybe an I, on a big exam question that we will find, and we're going to do the morning section's homework for them. Don't tell.